All right, hello everybody. Let's talk about the well-ordering principle, also known as the least integer property. And what this says, this is something that is obvious, is clear, but you got to actually see the subtleties of it. It's pretty important. So the statement is that every non-empty subset of Z plus contains a smallest element. So let's take a second and see if we can write that with some logic, some symbols. What does that mean? If a set A is a subset of Z plus and A not the empty set, okay, any subset of all I want of Z plus, then there exists some minimum value in A, and that's the important thing, that it's actually in the set A, such that such that for every other thing, everything else in A, M is less than or equal to it. Okay, that M is inside of A, and everything in A is greater than or equal to M. M is the smallest thing in the set. Okay. Now, subtlety there. It does have to be Z plus, for instance. If I got rid of Z plus and I made it Z, it would not be true anymore. Okay, so that's why the least integer property, to call it that, is kind of weird, because least integer? No, least positive integer is what we're talking about, okay? So that's one thing. If you replace it with Q, rationals, it's not true. If you replace it with R, not true. If you replace it with complex numbers, not true. If you replace it with anything but positive integers, basically, it's not true. Okay? Any of the normal sets. So it's a very special property of the positive integers, the counting numbers, 1, 2, 3, 4, 5. Let's take a look at a first example here. Take A to be the set 2, 5, 7, 12. Well, there's only 4 elements in that set. I don't even need to apply the least integer property. It's pretty obvious that there is a smallest element there, and the smallest one is 2, right? And that's the point, is that the least integer property is a fairly straightforward property, fairly straightforward thing, but the subtleties are what get you. So, hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So, if you're taking if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Here's a mathematical place where you might use that. Take A to be the set of all n in Z plus, where this thing, n squared plus 3n minus 200, is greater than 0. What in the world, right? Does there need to be an integer where when I square it, add 3n, and I take away 200, I get this thing is greater than 0? Does there need to be at least such one? And the answer is, I need to check two things. First, I need to check, is this a subset of Z plus? And absolutely it is. And that's just from right here, right? The set of all n in Z plus such that, well, okay, so therefore A is definitely a set of Z plus. But the other subtle thing we need is that A is not empty, right? Right in the thing, we had non-empty subset. So if you're talking about if you have an empty set, well, obviously there's nothing in it, so you can't say there is a minimum. So we actually would need to verify that this set is not empty. How would we do that? Well, I just need to show something's in there. There is an integer that when I plug it into this quadratic here, I actually get a number bigger than 0. And hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe, as I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example. You can pick anything you want, but if I pick, say, 100, if I take 100 squared plus 3 times 100 minus 200, Well, 100 squared is 1,0,0,0,0, 10,000, right? And then this is plus 300 minus 200, so that's plus 100. That's certainly greater than 0. When I plug in 100, 100 works. And 100 is an integer. And so what that tells me is that 100 is in A. In other words, A is not empty. Okay? So that proves that A is not empty, which then with the well-ordering principle proves there is a smallest n value. There is some small n that when I plug it in there, it will work. 1 does not work. 1 squared plus 3 times 1 minus 200 is less than 0. 2 does not work. 3 does not work. 4 does not work. But eventually, it does work. That's what the well-ordered principle really says. So that's a mathy example. We can also look at some non-mathy examples here. I can say that there is a youngest person watching this. Right? Think about that. Of course, and almost nobody would consider that wrong, but consider that an application. It's a set of all x in z plus. So we're assuming the lowest age a person could have is 1 in this example. And a person of age X watch this video. And that's my set. That is certainly a subset of Z plus because of the definition. It is also non-empty because you are watching it, right? Therefore, your age is in this set. So immediately, there is the age of a youngest person ever to have watched this video. Okay? And lastly, as well, there is a smallest number of Canadian coins where the value is $2.56, any value you want. Again, in that case, the set A would be the set X in Z plus, where there exists X coins that add to $2.56. And so, for instance, you could do a $2 coin, you could do two 25-cent coins, you could do one 5-cent coin, and you could do one penny. Oh, we don't have pennies anymore. We'll pretend we do. So how many coins is that? We have 1 coin, 2 coins, 3 coins, 4 coins, 5 coins. And so that proves that 5 is in the set A. Now, is that the best way to do it? Maybe, maybe not. And this is an important thing, is that the well-ordering principle or the least integer principle, it doesn't give you any idea what that solution is. It just tells you it exists. It doesn't tell you what the smallest way to do it or even how to find it. Like you go back to this one, the n squared one. I don't see any obvious way to do this except actually plug in numbers starting at 1 and keep going until you find one that's above 0. And I would use a calculator, certainly. I would probably use a spreadsheet even. But the point is that I can actually plug in values there, and eventually, I've proven here, eventually I will become positive. And whatever number the first one that becomes positive, that is the one that exists from the least integer principle or from the well-ordering principle. It has to exist. There has to be a youngest person watching this, and there has to be a smallest number of Canadian coins that add to $2.56. So we'll leave that there. Have a good one, and we'll see how we apply this in future videos. Have a good one. We'll talk to you soon. Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.